Today, Stanford University is one of the leading institutions in the sustainability movement. Specifically, Stanford has been at the forefront of adopting solar photovoltaic technology. Currently, new buildings such as the Night Management Center and Y2E2 are being built with solar PV systems on the rooftops. For our project, we looked into the multiple student initiatives to promote the use of solar PV technology, as well as what is being taught in the classrooms.
Different materials have different electronic properties. As you increase the number of atoms from a single atom to a bulk material, the electron orbitals of the atoms create energy bands. Each material has a filled valence band and a conduction band. In metals, this conduction band sits on top of or overlaps the valence band. This means metals are good conductors, since valence electrons can freely move into the conduction band. Insulators have a large band gap between the valence band and the conduction band. There must be a high input energy to excite an electron from the valence to the conduction band. Semiconductors represent the middle ground. They have a band gap, but it is not as severe as in an insulator. A typical semiconductor band gap is around 1 electron volts. Silicon's band gap is 1.2 eV. For a semiconductor, this means that a minimum energy input can excite an electron in the valence band to the conduction band. For instance, when the energy from a photon strikes the semiconductor, it excites an electron-hole pair. The hole, the lack of electron, remains in the valence band while the electron moves into the conduction band. If the electron has more energy than the band gap, it quickly settles down to the bottom of the conduction band by losing energy through thermalization. While some materials are intrinsic semiconductors, others work better when they are doped. There are two types of these extrinsic semiconductors, P and N-type. For P-type doping, engineers increase the number of holes by substituting an element like boron in the place of silicon. Since boron has 3 valence electrons rather than the 4 of silicon, there is an extra hole. For N-type doping, engineers increase the number of electrons by substituting an element like phosphorus. Phosphorus has 5 valence electrons rather than 4, and therefore provides an extra electron. This extra electron is weakly bonded to the rest of the atoms and therefore requires much less energy to be excited. Photons thus have a greater chance of exciting electrons to the conduction band. As light excites electron-hole pairs in both N-type and P-type semiconductors, the electrons and holes migrate across the p-n junction. However, this leaves behind a positive charge in the N-type material and a negative charge in the P-type material, forming a depletion region with a space charge. This produces an electric field which resists further diffusion of carriers. This is where we harness the power of PV. By connecting the two ends of the PV with a conductor, we allow the electrons to flow through and power a device before recombining with the holes in the P-type material.
The project is called SPORE, or Solar Panels on the Row, and the long-term idea is to get solar panels in every house on the row and also on every dorm on campus. And we hopefully would like to expand that to other places such as Treasurer Union and like other student-used buildings across campus. Right now, SSS is doing a pilot project on the roof of Story, which is where I live, looking to see how much PV potential there is, looking at the engineering specs, talking with solar companies, working with housing, the Office of Sustainability, and just like making sure we know what we're doing, and so that way, as we move forward, we with other houses and other dorms, we know the process and it can go that much more quickly. So it's going to be, Story is going to be basically a pilot project, and then we're going to expand out from there. A variety of solar companies. We don't really have anybody set yet because it depends a lot on how they're going to be compensating us with balance of system, Stanford's future plans for solar on campus, and other political issues. Currently, the project is based on an educational platform more than anything else, so we're not really looking at financials at this point in time, but we're going to be doing that as we look at cost of the installed power versus how much it will be producing, and if we can get a power purchase agreement or a PPA with the local utility to sell back power when we have excess, like, for example, over the summer, because there's not a lot of people in the houses. And so with Story House itself, it might not be such a big drop in the bucket, but as we expand throughout campus to all the routes on campus, then the impact would probably be much larger.
Hi, I'm Andrew. I'm a undergraduate working with the Stanford Solar Car team. The solar car is a really interesting project. The point of the solar car is to try to build a car that one person can ride in that will be able to go as fast as possible across the Australian outback, powered by nothing other than just the sun falling on the roof of the car. So these cars, you may have seen them, they're very streamlined, they're very lightweight, and they're made so that they can be powered off about the same amount of energy as a hairdryer, but can go up to 60 miles an hour on the freeway. So the point of the solar car team ostensibly is to win the solar car race. So every 2 years we go to Australia, and a bunch of teams from all over the world come to compete, and you race all the way across from north to south Australia. And of course, along the way of building this car, we build it from the ground up. Almost everything's designed and manufactured here at Stanford. Along the way, all of the team members learn a lot of interesting engineering. We learn about systems engineering, solar cells, batteries, motors, power electronics, all sorts of things that we're probably going to use in our future careers as energy engineers. In order to pick which types of photovoltaic cells we put on the car, we definitely have our primary concern is efficiency. So we have a limited amount of space on the top surface of the car that we can put the solar panels on, and we want to have as much power coming out of the array to push the car forward across the road. So efficiency is definitely our figure of merit. We're not looking for, cheapest cost. Our solar cells are donated, so we're not looking at cost or any other metric other than just the efficiency, how much power we can get for a given area. So when we were looking around, we're limited to silicon solar cells for the top of the car. And the company that makes the most efficient solar cells right now is a company called SunPower, actually started by Richard Swanson, who's a former Stanford professor, actually. And these solar cells are donated, and they're very special type of solar cell. They're crystalline silicon, actually monocrystalline silicon, so a single crystal of silicon across this solar cell. And the contacts are actually all on the back of the solar cell, so there's no shading from those little fingers of silver that extract the electrons. And so with that and some front texturing, which also reduces reflective losses, increases absorption of the cell, these cells are about 24% efficient. So that's one of the highest efficiencies on the market. And in terms of trade-offs, we weren't looking at cost since they're donated. And so we could basically shop around for whatever was the best silicon solar cell out there. There are a lot of challenges that you face in designing a solar car. The two most important design challenges are keeping the car as aerodynamic as possible, so it'll go through the air, and also keeping the weight as low as possible, so you don't have a lot of rolling resistance as you're on your tires as you're rolling along the road. So we have to be really, really careful never to have any excess components, anything that can be cut out of the car, we cut it out. So that means that our body is made almost entirely of composites, like carbon fiber, which keeps the weight really light. There's not a lot of metal, not a lot of steel. Any metal components are pretty much made of aluminum, which is a really low density metal, has a large strength to weight ratio. One of the great things about using photovoltaics as the primary power source for the car is photovoltaics have no moving parts, which means that the photovoltaics themselves are really reliable. So the parts of the car that could break down are probably going to be the motor or the power electronics, or if something could go wrong in the battery pack, which stores the electricity before it gets to the motor. So actually the solar cells are one of the parts of the car where after we make it, we don't have to think about it that much because they work so well. So solar cars are obviously very cool things. It's fun to see them on the road, or to drive in them, or to design them. But they're probably not going to take over the marketplace. There's not everybody's going to be driving solar cars around. First of all, it's not always sunny. Oftentimes it's cloudy and or night when you want to drive. So probably not going to be everybody's primary way of getting around. Additionally, if you do some really quick calculations as for how much power you can get out of these cars, it's not a huge amount. If you were going to take a typical sedan, maybe has about 2 square meters of top area, If you at full noon in June, you might be getting about 1,000 watts per meter squared of solar installation. And if you, so that's about 2 kilowatts falling on the car that you could have solar panels on. If you're going to put a pretty good crystalline silicon solar cell, you might be getting 20% efficiency out of that. Now you have 400 watts coming out of your solar array, and that's less than a horsepower. And if you think about most cars on the road today, they have engines that are rated up to 100 or 200 horsepower. So the amount of power coming out is so small, most people wouldn't buy a car that would go so slow, wouldn't be able to accelerate, wouldn't be able to go up hills very well. So probably solar photovoltaics as the primary way of powering cars isn't gonna be the future. Definitely, as more cars become electric, you can put solar panels on the top, and then hopefully the batteries can charge up when they're sitting or even when they're driving too, and that'll extend the range a little bit or reduce the number of places where you have to park in. So they can be a little bit of a range extender, but probably not the primary power source of future vehicles. However, that doesn't mean that designing and building a solar car isn't really important, because as part of the solar car we have to maximize everything for efficiency. The solar cells, the batteries, the power electronics, and the motor. And those are systems that are really important all across the energy economy. And so in terms of learning how to design these things always for efficiency, we're becoming better engineers, and when we go out and design a photovoltaic array that's just going to be stationary, not on a car, we know how to maximize the power for that. Or when we're making motors for cars that are run on batteries rather than solar cells, we can make those motors as efficient as possible. So solar photovoltaics, probably not going to be the future of automobiles. Definitely could be incorporated into some electric automobiles, but still a very cool thing to work on in terms of an engineering challenge.
We also talked about the idea that efficiencies that you might measure in the laboratory for a small-scale photovoltaic material, cell, can differ quite a bit. So these are the best results in the lab, and then these are the large area modulars. There's a big difference in efficiency. So that's why you'll hear things like, if I go back here, the world record efficiency for silicon is about 25%. There's the high end up here, which are the above the thermodynamic limit. Okay, so I mentioned in the last lecture I gave that there's a kind of thermodynamic limit of a single junction, a single PN junction solar cell, which is about 30%. This is actually called the Shockley-Pfizer limit. These are what they're called emerging photovoltaics, and you notice the word organic showing up a lot here. And I had a question at the end of 2 lectures ago about the organic, what we're going to be talking about. I'm actually going to be talking very briefly about organic photovoltaics. You'll notice that the efficiencies are really lousy. The highest is maybe about 10%. So why are people interested in organic? Why organic solar cells? The reason is because, again, like with second generation thin film, they can be made very cheaply. And especially with organic materials, there's a whole set of industries that use organic materials.
The price goes down 19% on every doubling. And it's been doing that since 1979, just inexorably like that. So we said, okay, it's probably going to keep doing it again. And those are those blue dots, okay? That's what we told Cypress would happen. Well, what I'm going to do here is I'm going to show you what actually happened. Now, you won't see economists do this. And you normally wouldn't see me do it either, except that the ending is kind of interesting. If you go to 2008, we were way above the learning curve, okay? We had deviated and this above the learning curve, and this was caused by a shortage of silicon, basically, in our industry. We were growing so fast, we suddenly overtook the chip industry as the largest user of refined silicon, and it took a while for capacity to catch up. That's a very short description of a very chaotic and horrible time.